Okay, let's dive right into this. Welcome to this explainer, where we're embarking on a super fascinating exploration of how projectile motion actually works. Whenever you watch a basketball arc perfectly into a hoop, or a baseball just absolutely fly through the outfield, you're actually witnessing a set of invisible rules that govern our entire physical world. Today, we are going to expose those rules. We're taking all those complex physics formulas and turning them into clear, visual concepts that just make sense. So here is our roadmap for today. We'll kick things off with vertical motion explained. Second, we'll look at the ideal horizontal motion. Third, enter projectile motion. Fourth, we'll see why only gravity acts downward. And finally, we'll track the complete journey of a flying ball.
All right, let's jump straight into part one, vertical motion explained, or simply the up and down.
To truly understand flight, we've got to pull movement apart into its basic building blocks. Let's isolate just one single dimension of movement first, straight up and straight down. Picture this, a really relatable action. Imagine you're standing outside and you toss a tennis ball straight up into the sky. What is actually happening in those few seconds? Well, the exact moment that ball leaves your hand, let's say with an initial velocity of 10 meters per second, it starts its journey with maximum force. Your hand just gave it all the energy it is ever going to get.
But instantly, an invisible battle begins in the air. As the ball climbs, it has to fight this relentless downward pull. Gravity and air resistance immediately start stealing its speed. So yeah, it started fast, but its upward velocity is steadily, constantly decreasing the higher it climbs. It's decelerating until it literally can't climb anymore.
And that brings us to a really crucial point, the number 0. At the exact moment the ball reaches its absolute maximum height, right before it gives up and turns around to fall, its vertical velocity drops to exactly 0. It freezes. Just for a microscopic fraction of a second, the upward fight is completely over and the downward fall is about to begin. Now lock that 0 in your mind because it's going to be super important in a few minutes.
Moving on to part 2, the ideal horizontal motion, or rolling forward. Okay, we've mastered the vertical up and down. Let's shift gears and focus purely on the horizontal. Imagine a ball rolling perfectly flat across the ground. Now, to make our math really beautiful and easy to grasp, we're going to step out of the messy real world and step into the physics world. See, in the real world, a rolling ball eventually stops because the ground rubs against it and the air pushes back. But in our ideal physics case, we get a superpower. We get to magically turn off ground friction and air resistance. We are operating in a perfect vacuum.
In this magical, frictionless universe, something pretty incredible happens. If you slide a ball forward at, say, 47 meters per second, it will stay moving at exactly 47 meters per second forever, because there are no invisible forces, no friction, 0 air, pushing back against it. Its horizontal speed remains absolutely constant. It'll just never slow down.
Let's move to part 3, enter projectile motion, combining the dimensions.
So, we have our two separate puzzle pieces, right? The vertical climb that fights gravity and the horizontal glide that goes on forever. Now for the real aha moment of this explainer. We are going to reconstruct those two separate one-dimensional movements into a single two-dimensional reality. This is the very definition of 2D motion. A projectile, whether that's a thrown baseball, an arrow, or a water balloon, flying in a beautiful curved path, is simply doing both of those earlier movements at the exact same time. It's moving forward on the x-axis and moving up and down on the y-axis simultaneously. It's literally two separate rulebooks operating independently on one single object.
Let's anchor this concept in reality using some exact numbers. Imagine you throw a ball incredibly fast, an initial velocity of 50 meters per second. But you don't throw it straight up and you don't throw it straight forward. You launch it into the air at an upward angle of 20 degrees.
This brilliantly illustrates how the magic of trigonometry breaks that one single throw into our two distinct dimensions. That 50 meters per second at a 20-degree angle, it's actually two speeds working together in disguise. It's an initial push of about 17 meters per second straight up and a steady push of about 47 meters per second straight forward. One throw, two hidden speeds. Next up, part 4. Only gravity acts downward, the forces at play.
Now that our ball is soaring through the air at that 20-degree angle, let's analyze the forces actively acting on it mid-flight. If we compare the two axes directly, a really stark contrast emerges. On the horizontal x-axis, like we established in our ideal physics world, there is zero net force acting on the ball. Nothing is pushing it forward anymore, and nothing is slowing it down. But on the vertical y-axis, the ball is entirely at the mercy of gravity, which is constantly aggressively pulling it downward. What we're looking at here is Newton's law playing out beautifully in the air. Because there is no horizontal force in our ideal case, that forward speed of 47 meters per second never ever changes. It is an absolute constant. But because of gravity, that initial vertical speed of 17 meters per second is always shifting, constantly being eaten away.
Finally, part 5, the journey of a flying ball, putting it to the test. To really cement how projectile motion actually works, let's trace our ball in slow motion from the exact second it leaves the hand to the moment it hits the turf. Our flight path has 3 critical milestones. We have the chaotic energy of the launch, the serene pivot point at maximum height, and the final impact of hitting the ground. Let's watch the numbers at each stage.
First up, the climb. The ball is traveling in a curve. As it gets higher, gravity saps its vertical speed. That upward energy drops from 17 down to 9 down to 5 meters per second. But notice the horizontal speed? It stubbornly remains at exactly 47 meters per second. The ball is still moving forward just as fast as the moment it was thrown, even though its upward climb is dying.
And here we are, back at the power of 0. At the very peak of the arc, the absolute highest point the ball reaches, the vertical speed is completely exhausted. It hits exactly 0 meters per second. This means, for a microscopic fraction of a second at the top of its curve, the ball is not moving up or down at all. The only motion happening in that split second is that relentless forward horizontal speed of 47 meters per second.
Then, of course, comes the fall. Gravity has won the upward battle and now accelerates the ball back down to Earth. The vertical speed increases again, going from 0 to 5, all the way to 17 meters per second right before impact. Now, in physics, we use a negative sign to indicate direction. So we say the velocity is -5 or -17 meters per second. That simple means the direction has reversed from up to down, and all the while it is still sailing forward at 47 meters per second.
So every single time you see a glorious sweeping arc in the air, you now know the secret. It's just a perfectly balanced dance between a forward momentum that refuses to quit and an upward momentum fighting a losing battle with gravity. Kind of makes you wonder, if these simple mathematical rules of projectile motion perfectly govern every single thrown object in the universe, what other invisible, elegant forces are shaping the physical world around you right now? Thanks for joining me on this explainer, and keep looking for the structure hidden in the everyday.